There's a data structure that can find any single item in a pile of a billion, and it doesn't get slower as the pile grows. One item or a billion, it takes the same amount of time. That should feel impossible. You've used it today. Every time you logged into a website, looked up a username, or your phone checked a contact, this thing was working underneath. It's called a hash map. And once you see the trick behind it, you'll understand why it feels like cheating. Let me start with a problem. Imagine a library with a billion books, and zero organization. Books just dumped on shelves at random. You want one specific title. What do? You start at the first shelf and check every single book until you find it. Worst case, you check all billion. Computer scientists call this linear search. The time it takes grows in lockstep with the size of the collection. Twice the books, twice the wait. Now picture a different librarian. You walk in, say a title, and without looking at a single other book, she walks straight to one exact shelf and pulls your book out. No searching. She just knows where it is. That's a hash map. And the magic isn't that she memorized a billion locations. The magic is a tiny piece of math she runs in her head. That math is called hashing. Here's the core idea. Instead of storing items in random spots, you run each item's name through a function, the hash function. It takes any input, a word, a number, a whole sentence, and spits out a number. That number tells you exactly which shelf, which slot, the item belongs in. So when you store it, you compute the number and drop it there. When you want it back, you compute the same number and go straight to that slot. No searching. Ever. Think about what that means. The location is calculated, not searched for. It doesn't matter if there are 10 items or 10 billion, computing the hash takes the same fixed amount of time. That's what we mean by O(1) constant time. Let's make it concrete. Say our hash function is dead simple. Take the first letter of a word and turn it into a number. A is 1, B is 2, and so on. The word apple hashes to slot 1. Banana to slot 2. Store apple in slot 1. Later, you ask for apple. The map runs the same function, gets 1, jumps to slot 1, done. It never looked at banana, never looked at anything else. It went directly to the answer. This is the trick behind so much of computing. Your programming languages, dictionaries and objects. Hash maps. Database indexes. Often hash maps. Caches, login systems, the routing tables in your network. Hash maps everywhere. But I told you our hash function was dead simple, and that was on purpose. Because that simplicity hides a problem. A big one. And this is where the magic gets dark. What happens when you store apple in slot 1, and then you try to store avocado? Avocado also starts with A. It also hashes to slot 1. Two different items, fighting over the same shelf. That's called a collision. Collisions are unavoidable. You have infinite possible keys but only a finite number of slots. By sheer math, different keys will eventually map to the same place. So the question isn't how to avoid them, it's how to survive them. The most common fix is called chaining. Instead of one item per slot, each slot holds a little list. When apple and avocado collide, they both live in slot 1's list, side by side. And here's the catch that most people miss. When you look up avocado now, the map jumps to slot 1 instantly, but then it has to walk down that little list to find the right one. If the list has 2 items, that's fast. No big deal. But what if every single item landed in the same slot? Now that one slot's list holds all billion items. Your lookup jumps to the slot in constant time, and then walks through a billion entries. You're right back to linear search. The magic is gone. So the entire performance of a hash map rides on one thing, a good hash function that spreads items evenly across all the slots. Spread them well, and every list stays tiny. Spread them badly, and you've built a slow list wearing a hash map costume. Now here's the twist that turned this into a real-world security nightmare. What if an attacker knows your hash function? What if they can deliberately craft inputs that all collide into the same slot on purpose? This is a real attack. It's called a hash collision denial of service, or hash flooding. Around 2011, researchers showed that many popular web frameworks were wide open to it. PHP, Java, Python, Ruby, all vulnerable. The attack was brutal in its simplicity. A web server takes the form data you send and stuffs it into a hash map. The attacker sends one request packed with thousands of keys, all engineered to hash to the same slot. Suddenly that hash map degrades to a giant linked list. Inserting each key forces a walk down the whole chain. What should have been instant becomes quadratic. A single small request could pin a server's CPU at 100% for minutes. You didn't need a botnet. You didn't need to flood bandwidth. One laptop, a few cleverly chosen strings, and you could take down servers by weaponizing their own hash maps against them. The data structure DDoS'd itself. The fix was elegant. Modern languages now use randomized or keyed hash functions. They add a secret random seed when the program starts. So the attacker can't predict which inputs collide, because the hashing changes every run. That's why languages like Python randomize string hashing by default now, and why robust systems use functions like SipHash, designed specifically to resist this kind of attack. The Magic Librarian got a security upgrade. So step back and look at the full picture. A hash map gives you near-instant lookups by computing locations instead of searching for them. That's the genius. But it leans entirely on collision staying rare and well-distributed. Get the hash function right, and you've got something that feels like magic, constant time in a billion items. Get it wrong, or let an attacker control it, and the same structure becomes your slowest bottleneck and your biggest vulnerability. That's the real lesson hiding inside this everyday tool. The most powerful abstractions in computing aren't free magic. They're trades. And the engineers who truly understand them are the ones who know exactly where the magic breaks.